Alrighty, so welcome back to one of my short little lessons here. Today we're going to be looking at the classic problem of a ballistic pendulum. So here we say a marksman fires a bullet into the block of a ballistic pendulum. The block, with the bullet embedded, swings upward. After finding how high the box swings to the top, the marksman can calculate how fast the bullet was traveling. Derive a formula for the bullet's initial velocity. So whenever we're looking at problems like this, we're looking at ballistic pendulum problems, we actually want to separate the problem into two different parts. The first part, when the bullet is fired and then gets embedded into the block, this is actually a collision. Because it's a collision, we can use the conservation of momentum to actually kind of solve things out here. So that's the first part of it, is we just have this collision. But due to this collision, kinetic energy has been added into the system, or the kinetic energy from the bullet has kind of transferred with the block, and now the block is starting to swing. And so we really want to zoom in on what this block itself is doing. And so the block is going to swing upward until it gets to this top moment. At that point, we have a conservation of mechanical energy problem. And so it's these two different problems that we're going to put together in order to actually derive our formula here. And once again, what we're trying to find is the initial velocity of the bullet. So as we zoom out, what we're going to see over here, and zoom in a little quick, a little bit closer, is a diagram that kind of goes over what's happening. So the first thing that we have is we have this bullet that's coming in and it's going to hit the pendulum. And as you can see here that we have this conservation of momentum because this is a collision. And so as the bullet comes in and it hits this piece, we have this conservation of momentum. So this would be the collision portion. But once we get through the collision, once they're here, now this box is swinging, and we know that when we have something swinging up, we're going to the top, coming back down, we can use conservation of energy at this point. Notice as I box those off, this in-between part is really both of them. And so this is really important. So often, students want to label just initial and final. That's what we do most of the time. But unfortunately, the final part of the collision is the initial part of the energy problem. And so it's actually going to be a little bit more beneficial here to label things maybe 1, 2, and 3 so that we don't get confused with our initials and finals. So let's go ahead and just start by writing this conservation of momentum problem and see what that does for us. So here we have conservation of momentum needs to equal 0. So we're going to do our momentum 1, and we're going to set it equal to our momentum at 2. So we're talking about 1 and 2 here. So our momentum 1, we have the two pieces of our system, which is the bullet and its initial velocity, plus the block and its initial velocity. So I do want to notice that I'm going to be using little b for bullet and big B for block. Then, after the collision, they have actually connected together, and because they are connected together, they have the same velocity. So we can just say the velocity at 2, so the velocity of them together, times their combined masses. And this is because it is a perfectly inelastic collision where they go ahead and combine together. As we look at this, once again, this is what we're trying to solve for. So we can actually go ahead and isolate that. The block originally had no velocity, so that cancels out. So we get the mass of the bullet times the initial velocity. We can go ahead and divide by the mass of the bullet. And there you have it. We've actually gone ahead and isolated the initial velocity. So some people always like to stop here. We have an answer. The problem is inside of this answer is a quantity we don't know. We can't put this inside of our answer because it's a quantity that we aren't easily able to find. It's not readily there. And so this is why we have the second half of the problem. The second half of the problem is going to help us figure out what is that velocity at 2? How much velocity does the block and bullet kind of combined piece have after that collision. That's what we're going to be looking for in order to find out what was that initial velocity. So now we can come over and do a conservation mechanical energy statement. And so we're going to do the mechanical energies at both. Here, to get us started, we're going to do the mechanical energy. So we're going to start with gravitational potential. Well, because it's at the bottom of its swing, we're just going to go ahead and call that 0. That's where we're going to zero out our potential energy. Then its kinetic energy, we know it's 1/2 the mass. So the mass here is the combined masses, and the velocity squared. And then this is that velocity at 2. This is the velocity that we're actually trying to find. So our total mechanical energy at this point is just that kinetic. So once again, that was the mechanical energy at this point. So once the bullet has been embedded, when this is about to start swinging, how much velocity this guy has, what we're looking for. And so we did a full mechanical energy statement for it too. We're also going to do one for 3 now after it's swung and it's at the top. Notice that it does tell us at the top, we should know this, but that the velocity is going to be equal to 0. And that is because we know that at the top of the swing, it's momentarily at rest before it starts to swing back down. So here, we're going to look at the gravitational potential. This one does have gravitational potential because it's no longer at the bottom of the swing. So we're going to represent that as those combined masses. And then just GH, our normal expression for potential energy, gravitational potential. If we look at the kinetic, as we just said, it has 0 velocity at the very top as it swings back down. So its kinetic is equal to 0. So the total in this case is just that gravitational potential. So now that we have those, because the conservation of energy, we know that we can go ahead and set these equal to each other. As a reminder, this is the quantity we're trying to find, so we can plug it into our other expression. So looking at this, trying to solve for V2, I immediately notice that the masses cancel on both sides, giving me this phrase here. And with a really quick rewrite, we find out that V2 is actually just equal to the square root of 2GH. And this is something you may have come to quicker. Once you've solved this problem out once, you can typically go back to this. If those are really the only things that you're dealing with is the kinetic energy at the bottom, potential energy at the top, we get this phrase a lot. And so you may have seen this one before and been familiar with it, or you do all of the work out like we've done before. However, now that I have it, we're ready to go ahead and plug it in. So at this point, we can go ahead and plug that phrase in. So we're going to do the velocity of the bullet at the bottom, that initial that we're solving for, is equal to the square root of 2GH times those combined masses over that initial mass of the bullet. So this is why I like ballistic pendulum problems, is because it really allows you to split the problem into a conservation of momentum and a conservation of energy. When you start looking at elastic ones, you're going to find out that elastic collisions have that conservation of kinetic energy during the collision. And because of that, students often want to just go ahead and do conservation of energy all the time. But you have to think about what is actually happening. Here, we just have a collision, so all we can focus on is the momentum. And because they stick together, we know it's not elastic. We actually know it's perfectly inelastic, which means that it's going to lose some of that kinetic energy. And it's losing some of that kinetic energy and kind of the thermalness that's going on there, the actual process of embedding. And then we have, now that we figured that out, we have this system here. And because we have this system of a box, once it figures out its velocity swinging, we can do that conservation of energy at this point. So separating the whole process into the different things that are happening. Physically, we're having a collision, and then we're having a swing.